All right, thank you. So I'm Justin Johnson. I'm going to tell you a little bit about my work on from recognition to reasoning. And as John said, I just joined the University of Michigan at the beginning of September. So I have to admit that this work has not actually been done at Michigan. But I'm hoping I'll come back next year and tell you all the cool stuff that I've done in the year since then. So I work broadly in the area of computer vision. And computer vision is, unsurprisingly, the task of building machines that can see. But what does it mean to see? Well, one core task in computer vision is that of perception, or recognition. And that means that we want to build systems that can look at images or other types of visual data and tell us what they see in those images. So here we're showing an example outputs from one of these state-of-the-art perception systems. And these are working really well these days. So we can look at these examples at the top. This is from a network called a panoptic feature pyramid network. We can look at these examples at the top, and we see that these computer vision systems can go out and carve us and say that there are maybe 4 people in this image, and carve out the exact pixels of the image that tell us which pixels correspond to each person. We can do this for people, we can do this for zebras, we can do this for grass, or on the bottom you can see we can do this for cars and roads and other types of situations. Now, this perception problem is really important because it forms the core of allowing computers to work with broad sorts of visual data. And even from the talks today, we've seen that perception is a really critical piece of robotics and self-driving cars because systems need to be able to understand what they're seeing. And perception has gotten very successful in the last few years due to the use of large, deep neural networks. But although perception is really important, I think that it's important to remember that it's just a small slice of the full computer vision picture or the full AI picture. So in my research, what I like to do is to try to use the tools that have been useful for perception and use them to set up new types of tasks that drive towards more broad sorts of visual intelligence that require not just understanding what we see in images, but also somehow reasoning about the things that we see to solve more complicated tasks. So to give you a sense or a flavor of what this means, I want to talk briefly about 3 concrete problems that I've done that require integrating a perception system with some kind of more in-depth reasoning system. So the first is the task of 3D shape prediction. So we've seen in the past that there's these classical perception systems really treat the world as if they were a grid of 2-dimensional pixel values. So here on the left, we're seeing the outputs of a state-of-the-art perception system called MaskRCNN. And MaskRCNN looks at an image, and it draws 2-dimensional boxes in the image to tell what objects are present. It gives them labels, and it tells which pixels correspond to each object. And it does a really good job, right? It can draw boxes around all these people on the beach. It knows that there's people and benches, and it does a great job at labeling all of these things. But MaskRCNN fundamentally is missing something really important about the real world. And that's the fact that the world is not actually a 2D grid of pixels. The world is 3-dimensional. And we should be able to build systems that can reason not just in 2-dimensional pixel space, but also in the 3-dimensional world space that was used, in which these objects actually live. So this past year, I built a system called MeshRCNN that moves from masks to 3D triangle meshes. So what this system does is it looks at 2-dimensional images and predicts not just 2-dimensional boxes, but gives us a full 3D shape of all the objects present in the scene. Now, this actually requires some non-trivial reasoning about the scene, because predicting 3D shapes from 2D images is a fundamentally ill-posed problem. And we can't understand, just from a 2D image, we don't know what's on the back of those shapes. But nevertheless, our system is able to look at these 2D images and actually tell what objects are in the image, and as well as predict these full 3D shapes for all the objects in the image. How does this work? We train a big deep neural network, because that's what everyone's doing these days. In particular, we use a fancy type of neural network called a graph convolutional neural network that operates over the vertices and edges of a 3D triangle mesh. The details are not super important. But what is interesting is that after we train up this big thing, it's able to give us some really non-trivial results at predicting 3D shapes from 2D images. So in this example, we can see that this system can, one, detect multiple objects per scene. We've got a chair, a couch, a table, and another table. Another interesting is that this system can actually predict the occluded parts of objects. So here, in this example, we can see that there's a dog in the front of the image, and a couch in the back of the image. And even though the dog is covering up part of the couch, the system is still able to predict the 3D shape of the couch that's covered by the dog. Unfortunately, we cannot predict the 3D shape of the dog because we only trained this thing on a data set of IKEA furniture. And maybe once IKEA starts selling dogs, then our system will be able to detect those too. But another interesting point about this system is that it shows that some of the failure modes of 2D perception also bleed over into failure modes of 3D recognition. So here on the left is applying a 2D perception system to this scene. And we can see that the 2D system misses some parts of the bookshelf. And on the right, our 3D perception system misses the same parts of the bookshelf. So it's interesting to see that those failure modes actually carry over. So that's our first task of 3D shape recognition. This requires a little bit of reasoning, a little bit of generalization beyond the raw visual domain. But it's still fundamentally a perception problem. So let's think about another task that requires more robust intelligence. Right? In this task of 3D shape prediction, our networks can only do one thing. The only thing they know how to do is predict 3D shapes of objects. Whereas a more general AI system should be able to adapt its capabilities on the fly in response to new types of situations at test time. So as an example of a system that can do this, let's talk about another task of visual question answering. So in visual question answering, what we want to do is present the system with an image and a question. And the question can ask something very complicated about the image. In this example, how many spheres are left of the big sphere, and the same color as the small rubber cylinder. So you can imagine that in order to answer this question, the system needs to both understand what is being asked in the text of the question, it needs to understand it needs to visually perceive or recognize what is present in the scene, and then it needs to combine the perception of what it saw in the scene with its understanding of what the text was talking about in order to actually arrive at an answer to this question. And you can imagine that a system that could answer very general, complex compositional questions such as this could now adapt its behavior flexibly at test time to do all sorts of interesting things involving visual data. So we built a system that can answer these type of rich compositional structured questions. And it works in two parts. One, we have one neural network called a program generator, which reads the text of the question one word at a time, and then outputs a structured compositional program or plan, which is how we will choose to answer this question. So in this example, are there more cubes than yellow things? Well, what we need to do is first count the number of cubes, then count the number of yellow things, and then compare them. So the system emits a little program that contains those basic steps of reasoning. And now we have a second component called an execution engine, which actually is going to execute that program on the visual scene, perform each of those basic steps of reasoning, and then arrive at an answer to the question. Now again, we're going to model both of these components with neural networks. So the program generator will be a little recurrent neural network. But the interesting part is the execution engine. The execution engine is an example of what we call a modular neural network. And so the way that this works is that the network contains a set of neural network modules, each specialized to one of these basic fundamental components of visual reasoning. So this execution engine, for example, contains little neural network chunks that know how to look for yellow things, or look for large things, or knows how to compare counts of objects. And now, given the predicted program from the program generator, what this will do is it will assemble the neural network chunks from the execution engine into a custom neural network that is specialized in its architecture for answering the particular question that was present. And then, of course, we run through this second execution engine and arrive at the answer to the question, like yes. And you can imagine that this kind of explicitly compositional, explicitly structured form of a model might give us the flexibility to answer very complicated questions and to generalize to new types of questions that use the same basic primitives of reasoning in novel ways at test time. So that gives us two tasks, one of 3D shape prediction and one of visual question answering. And we've seen that as we moved to visual question answering, our systems became more flexible, and they were able to answer more complicated types of queries about the world. But both of these systems so far have made the assumption of a static world. They operate on just a single frame of visual input, and they only capture a snapshot or a moment in time of what the world actually is. But we know that the world is not static. We know that the world is dynamic. And a truly intelligent, truly visually intelligent AI system should be able not only to work on static snapshots or static moments in time, it should be able to reason about how things can unfold in time. And it should be able to not only perceive the environment, but also interact with the world and actually change the way that things unfold over time. So as a third task that's more recent work, I've been interested in this new task of physical reasoning. So here, we set up a set of physics puzzles that neural networks need to solve. So the way that this works is that the system is presented with some initial world state. Here we see a green ball on top of this kind of gray lever. And the system is given some kind of goal that it needs to get the world to achieve. So in this case, what we need to do is make the green ball touch the blue ball. And the physics of and then in this little world, the black objects are static. They're sort of bolted to the scenery. And the gray and the blue objects are all dynamic. So those can all move around as physics will play out. So in this example, if we were to just hit play on the physics, then the gray lever that the green ball is currently sitting on would just fall to the ground. Now somehow, the system is then tasked with changing the state of the world in a way that will cause this goal state to be achieved. So then the system needs to perceive the world. It needs to reason about what are the objects in the scene. It needs to think about the potential physical interactions of that object. And then it needs to manipulate the world to cause this target goal to be achieved. So again, this is a much more flexible and much more general sort of reasoning than these previous systems that operate only on static snapshots. So in this case, the system might choose to stick these two red balls into the scene such that when physics plays out, the goal will be achieved. So the system makes this action of adding these new objects to the scene. Then we press play on physics. And we see that by cleverly choosing exactly where to stick these balls, then this system can cause this non-trivial goal state to be achieved. But of course, we didn't just build one physics puzzle. This is actually a large suite of lots and lots of physics puzzles. And now the idea behind this is that in this FIRE benchmark, as we call it, we need to train on one set of physical puzzles. And during training time, systems get to interact with these different types of physics puzzles and learn how to solve them. And now at test time, systems should be able to generalize their knowledge of how the physics in this world works, and then solve new physics puzzles at test time in very, very short amounts of time. Unfortunately, I have not solved this problem yet. Right? This is sort of initial work where we set out this task or this benchmark for measuring physical reasoning. But I think we don't actually have a good solution to this problem yet, because it involves both understanding physics and then reasoning about it very quickly at test time. So that gives us these three example tasks that move from perception and recognition onto more complicated reasoning tasks. So we saw 3D shape prediction, we saw visual question answering, and we saw the beginnings of a system that could perhaps perform physical reasoning. And hopefully we'll come back next time and tell you some amazing results on this physical reasoning benchmark that I put forth. So with that, I'm happy to take a few questions.
Hello.
Yeah.
Over here to the far left.
Oh, yeah, go ahead.
Have you looked at this against any existing sort of game engines like Unreal or any of these like physics engines that are involved in the gaming world and compared it against those?
Yeah, so the question is, have we looked at existing physics engines like Unreal? And actually, we did use an existing physics engine called Box2D, but it was a 2D physics engine. So I think writing your own physics engine is not something that you want to get yourself into the trouble of doing.
That's my point, is taking the existing out of the box stuff and modifying those. And how does this relate to those? You know what I mean? We don't have to reinvent the physics engine when there's tons of gamers playing them already.
Oh, yeah, so we're not reinventing the physics engine. We're using an existing off-the-shelf physics engine called Box2D. So something like Unreal works in 3D. We wanted to not, right? For this problem, we wanted to focus on the essence of 2D reasoning, of physical reasoning. So we wanted the simplest sort of scenario that requires physical reasoning. And then there we thought that focusing on 2D physics would be simple enough to let us focus on the problem of reasoning. And in the future, if we could get this to work, then I think extending to 3D and more realistic physics engines would be an interesting direction to look at.
Sounds good, thanks.
There's a question over here.
What are the benefits of creating a 3D model from 2D image versus just working with a 2D image?
Oh, the question is, what is the benefits of creating a 3D model from a 2D image? Well, I think that I think there's a lot of applications. So anytime you have a system that needs to interact with the world, then it needs to understand the 3D structure of the world upon which it's going to interact. So for example, something like a self-driving car needs to understand not just that there is a car and it has these pixels, it needs to understand the 3D structure of how those objects are positioned in space. Another important application here is something like virtual or augmented reality. So in augmented reality, if we want to have systems that can overlay new virtual content onto the visual world that we see, then what they need to be able to do is understand the 3D structure of the world such that we can now blend virtual content seamlessly with the real world. Yeah, question?
Where does the second problem we discussed, where does it start to fail? Does it start to fail when you add too many parameters, or is it like when there are specific parameters that are difficult to process?
Yeah, so the question is, when does this visual question answering system start to break down? I think it starts to break down once you require new primitives of reasoning that were not seen previously. Right? So in the system that we saw, it kind of works in this closed blocks world scenario. It knows about blue things, it knows about purple. I don't think it knows about purple things. It knows about blue things and green things, but because it never saw purple, if you ask it a question about purple, then that's a novel symbol that it's never known how to ground in the past. So anytime it requires novel primitive elements, then we're in trouble. So this system requires us to inject some expert knowledge about what are the primitives. But I think figuring out systems that can discover novel primitives for themselves based on the data that they see would be an exciting next direction for that area of research. We have time for one more?
Can you see the different downstream tasks that you saw overlapping in the future? So for example, having a Q&A system to answer questions in physics or something like that?
Yeah, so a question about downstream tasks. So for something like Q&A, I'd like to be able to ask Siri, like when I get home, if the temperature is above 75 degrees, then turn on the air conditioning and start preheating my oven for dinner. That's a very interesting compositional task that I'd like systems to be able to solve. And I'd like them to be able to do that without having to hand program explicit rules for all those different subproblems. So that's where I see the main application of that sort of work.
Thank you, Justin.
Yeah, thank you.